everybody. Second day here at CuttingGardens Lyon. I just wanted to show you our setting here, put together.
And I think Alex, who designed this whole space with the complex Kapharnaum art collective, is going to explain this much better than me. This is the movie they shot on site. Watch this.
C'est une première expérience de congrès décentralisé, c'est-à-dire qu'il est distribué dans 21 antennes dans le monde. Et donc on est déjà dans un nouveau format et on a proposé une installation un peu différente, des choses qui sortaient du cadre habituel. On a décidé de travailler avec une compagnie artistique nationale qui s'appelle Kapharnaum, qui nous a aidé à monter différentes infrastructures qui servent à sensibiliser sur la transition énergétique et favoriser de la convivialité d'une manière atypique pour essayer de décaler un petit peu le regard des participants.
Super good, food great, the construction is amazing, a great event.
Le cadre est génial, les structures en bois, tout ça, c'est la première fois que je vois ça à une conf.
Non mais c'est vraiment joli. Le petit bar là-bas, café, c'est vraiment hyper agréable. C'est la plus belle conf scientifique
Du monde.
que j'ai faite.
On a trouvé le mot pour obtenir notre plat à la cantine, c'était miracle. Ça représente bien la conférence.
La nourriture est très bonne, variée, suffisante, originale.
Des vrais plats végétariens, une vraie cuisine végétarienne, c'est bien, c'est rare.
De mémoire de séminariste, c'est la première fois qu'on mange aussi bien.
Oui, c'est vrai que ça renouvelle un peu parce qu'on a toujours l'habitude d'avoir des petites portions avec beaucoup de choses à jeter, etc.
Donc ouais, moi j'aime beaucoup le principe d'avoir des grandes tablées, la sorte. Par exemple, je suis arrivé tout seul et c'est un peu le meilleur moyen de discuter, rencontrer plein de gens différents et d'apprendre des choses aussi.
On mange mieux et on discute plus en plus. Enfin, je trouve le contrat est rempli, ouais. Haut la main.
C'était pas forcément évident de faire leur vaisselle à des scientifiques qui ont l'habitude d'être plutôt reçus et qu'on s'occupe de tout pour eux. Il y a aussi un gros travail qui a été fait sur les repas, donc cuisiner sur place. Donc on pouvait aussi rencontrer les gens qui nous préparent des plats, qui nous servent. Et on a pu intégrer aussi par exemple les posters pour qu'on puisse mixer ces moments informels et puis des moments formels, que ce soit un peu une sorte de transparence ou de porosité entre ces deux mondes-là.
I really enjoyed seeing my former postdoc advisor washing dishes.
That's the first conference that I see that is like that. We are not like just eating and then waiting for someone to clean our things.
It's good to remind people that we are collective animals and that we should behave in a collective way.
I'd love that you stay here for the next few months.
Yes, me too.
Il y a une volonté en tout cas d'ouvrir le débat. On s'est inspiré de graphiques scientifiques qui ont été mis en forme pour attirer l'œil du scientifique, mais être regardé peut-être différemment avec un peu un dézoom et une prise de distance. Et qu'est-ce que ça nous fait ressentir et de toucher peut-être aussi pas que l'intellect mais l'émotionnel.
Hi everyone, sorry. My name is Marie-Constance Corsi and I'm really thrilled to be here to host this session on challenge and opportunities in real-time EEG processing and classification for BCI. That one actually is the prize of the shortest title for cutting EEG. So just before starting, I just wanted to give you some elements of context, in particular for those who are not familiar with the BCI domain. So briefly, BCI, or Brain Computer Interface, consists in devices that aims at translating the brain activity into commands. And for that, there are many applications, of course, to control real objects, but also to communicate with someone else. But when we see it as a black box, it's also interesting to see which are the steps actually that compose the BCI system. And for that, we are mostly interested in 4. The first actually consists in trying to record the brain activity. And for that, here in this session, we'll be more focused on non-invasive tools. So, of course, I mean, most of the protocols rely on electroencephalography, but we could also cite other modalities such as NIRS, fMRI, and MEG, or even a combination of different modalities. Then, once you have acquired and recorded this activity, you can extract the information of interest called features. And depending on the application or the paradigm you're using, you can be interested either in the spectral information or the temporal information. So, for instance, we could imagine for the like multi-imagery-based BCI, I could be interested in the spectral information. So we'll extract the power spectra in a dedicated sensor in a specific frequency band of interest. And then, based on this information of interest, you can perform what we call a classification. So to discriminate the different conditions performed by the subject. And for that, you have plethora of tools, and you will see with the presentation you have today, there are many, many more, but perhaps just the simplest one would be the LDN or SVM, for instance. So once you have classified data, and for instance, for 2 tasks, you have like a binary information, 0 or 1s, and based on this information, you could provide to the subject an information called feedback that could be either a visual, an auditory, or a sensory information. And in this way, you have like a closed loop system. So I'm just like giving some elements of vocabulary that can be used during this full session. So based on that, you know that we have many applications for the BCI, but we need to also to acknowledge some limitations. And one of them is that between 15 to 30% of the users cannot control the BCI device, even after several training sessions. It corresponds to the BCI inefficiency phenomenon. So during this session, we'll try to address such challenges, but by different perspectives, either from the machine perspective, but also from the user and mostly patient perspective. So basically, we are going to have like the same structure as yesterday with different talks, followed by 10 minutes of local brainstorming and then Q&A. The only difference from yesterday will be on the general discussion that will be shorter from the brainstorming part, but we will see it afterwards. Then another item, because I can't share my screen tonight, but it's fine. I have also a link that will provide it to you afterwards, because we created a GitHub page in which we'll see afterwards all the slides prepared by our beloved speakers. And also some surprises for you afterwards. I'll try, actually, thanks to the wonderful team here with Christelle and Anaïs, to collect all your questions. And from that, we also provide some FAQ afterwards. So enough talk from myself. It's time to introduce our first speaker, Reinmar J.KOBLER. So after his PhD at Graz University on MEG-based kinematics and encoding in sensory motor task in 2020, he started a postdoc at Riken Center for Advanced Intelligence Project and Advanced Telecommunication Research Institute Information at Kyoto from Japan. We're super glad to have you here today. And he's mostly interested in new machine learning methods based on undoubtedly deep learning approaches, but not only. So now he'll give you a talk on geometric DL approaches for BCI. Reinmar, the floor is yours.
Thank you very much, Constance. Thank you very much for the introduction. I hope I'm audible. I should share my screen again, right? Just a second. So now you should see, hopefully, some slides. So, okay, sorry, just one quick thing. So I hope by now everything is set up correctly. So thank you very much for your introduction. And today's talk, actually, I will focus mostly on combining 2 things, which are deep learning and geometric learning specifically to tackle one challenge, which is inter-subject and session transfer learning in BCI. As Marie-Constance has already said, we have typically some effects localized in either time, frequency, and space, or frequency and spectral domain, that we look into EEG or some other brain imaging technique. And for example, also multimetry, we have time-locked after a person starts their multimetry task, usually some power increase in like typical alpha and beta frequency ranges, followed by power increases in the time domain and the spectral domain, and they are usually localized in the hand or feet area, right hand area and the left sensory motor cortex. So we have these temporal, spectral, and spacing effects. But what we actually measure in EEG is like a mixture of sources, not only EEG, but MEG, ECOG, and also LFP. So what we want in BCI and in other domains in this setting, we want to use these observations, let's say short segments of data, to decode, for example, multimetry. For example, right-hand multimetry versus feet multimetry. In this setting, the coupling is already quite well understood, but in other settings, it's not so well understood. And there is actually quite some challenges with EEG data, which is first, usually we have not so good signal-to-noise ratio or rather poor. We typically have differences across the subjects or individuals, and the effects that we study are often non-stationarity. So when we think about this ERD or ERS maps, we usually report these findings relative to some baseline. That's mostly due to these non-stationarities. And typically, we also have quite little data. So not many users, not many subjects, because it's just simply expensive, time-consuming to collect data. And as I said before, the coupling mechanism is not always very well understood, and also specific to a certain task. Lastly, we also have quite some outliers that we often encounter, which are due to technical or also neurophysiological sources. So we have quite some challenges that we have to consider. And in this context, what are our requirements for a BCI? And I'm mostly focusing on the machine learning part. So what are the requirements for the classification or decoder system? So ideally, we want to have a classifier or decoder that also is able to extract features, so learn these temporal, spatial, also spectral localized events. It should be robust to outliers, to these artifacts, but also to the scarceness of our data. On the other hand, it should be also interpretable because of these outliers and artifacts. So we want to make sure if our decoder is actually utilizing useful or meaningful information. And of course, it should generalize to unseen data and ideally also to other subjects and days. In recent years, typical examples of decoders that have become more and more popular are on the one hand, of course, deep learning, which has a nice advantage of also being able to learn the features via feature extractions. Sometimes, unfortunately, not so robust because of many parameters that need to be optimized. And interpretation is also not a strength per se. Generalization is usually recently quite good. On the other hand, what's been also very popular in BCI has been Riemann and geometry-aware methods, which need manual feature extraction before, but have robustness, have shown to be quite robust, and also recently shown to be interpretable, which in many settings, like large-scale EEG data sets, perform on par, more or less, with deep learning methods. And also, maybe here is an interesting example of mental workload estimation competition, where you can see in red performance on the validation set and then actual performance on the test set, and you can see quite some performance drop for deep learning-based methods, which is again this indication of robustness. Whereas this proposed Riemann and geometry-based methods don't have this extreme performance drops. So what are these Riemann and geometry methods and what do they utilize? I guess not so many people are familiar with this kind of direction. First of all, they basically work in the space of covariance matrices, and thereby they usually reduce the dimensionality. So if you integrate the whole temporal information via computing covariance, you reduce actual dimensionality quite a bit, usually. And on the other hand, they are also actually consistent or ideal models for investigating power modulations with log linear coupling between the EEG, for example, X, and the target Y, which is the case, for example, in motor measuring. And they have this nice invariance property to linear mixing. So that sounds maybe a bit abstract. Let's maybe look dissect it with a specific example. So if we have a segment of EEG data, xj, then compute the covariance matrix, we see like a very simple covariance matrix here. Then we could, as people often do, we compute, for example, ICA or some other linear decomposition in the source space, and then we can again compute the covariance matrix, just in a different space. And of course, we can do this for another observation, another segment of EEG data in the channel space here, but also in IC space, and we get 2 points. So in this high-dimensional space. So we can naturally compute the distance between these 2 points. For example, Euclidean distance. And what we will find is that the distance in this space, between these 2 points in this space, will be not the same using the Euclidean distance. So we don't have this invariance to this linear mixing. However, covariance matrices, so excluding degenerate cases, are typically symmetric positive definite. So they are on a specific cone-shaped manifold in this high-dimensional space. And there has been some nice metrics proposed for this particular space. For example, the final variance metric. And if we use this metric to compute distances in channel space, but also in source space, we'll find that the distance is the same. So this distance on this manifold has this nice invariance property, which is quite useful. So it means that if we compute distances in channel space or in source space, it doesn't matter. So then on the other hand, as I mentioned before, we have this challenge of generalizing across sessions and subjects, which is quite severe actually in the EEG BCI systems, but also in other neurotechnology-based systems. And this is mostly due to distribution shifts, which are caused by mental state changes, so mental drifts, but also external drifts due to changes in the impedances of electrodes or artifacts. And they manifest in these distribution shifts, which you can think of, again, maybe some segments of EEG, you feed them through some feature extractor, for example, the standard bandpass, which extract broadband EEG activity or alpha-beta band EEG activity, and then you compute the covariance matrices. And what you will see is when you plot these covariance matrices, for example, using t-SNE or some other method to visualize this high-dimensional space in a 2D space projection, you will see that the distribution for each subject is they're all scattered all over the place. So we have quite some shifts in the distributions across subjects, which are color-coded here. And of course, this is very difficult for a shared or like common classifier to separate the labels in this data. In the intersession setting, it's there, but not so severe typically. So the gold standard that has been used for a long time is to use just calibration data on each new day or new session, and then fit the day or session specific model. So a simple model, because usually we have quite limited data per day, which of course has poor scalability and utility because you always need to have labeled calibration data, which is expensive to record. Yeah? And an alternative, which has been getting more and more popular, is to utilize data of other sessions or subjects and do something that machine learning people call domain annotation, or ideally unsupervised domain annotation, where you then don't need any label information for the new day or for the new session or new subject. And ideally, this is unsupervised, so new label information required for the new domain, and source free, meaning that you don't need any data from the other subjects when you do fits the model to the new subject, the new day. And ideally, since we're talking in this session about BCI, ideally you can do this also online. So now we have established this kind of challenges and problems, and how can geometric deep learning help in this setting actually? So what we consider is, again, some input space, for example, segments of EEG activity. We have some feature extractor, which extracts some latent representation of features, which we want to feed through a simple classifier, for example, to predict our labels. And first objective that we want is like standard deep learning. We want to have a feature extractor which can learn from the data, which we can feed to the data. For example, some convolutional layers or convolutional nets, which actually improve SNR and also extract activity of relevant sources for our task. Then on the other hand, we want to address these distribution shifts across days and subjects. So one option is to actually do explicit alignment of some moments of these different domains in this latent space that we have just extracted. And lastly, because we have this term geometric here, what we all want also is to gain this or utilize this robustness property of this SPD manifold equipped with the finite variance metric. Specifically, we want to constrain the latent space to the SPD manifold to benefit from these properties. Yeah. Okay, so for the latent alignment, there's a idea is very simple. In terms of explicit alignment, you want to align some moments, for example, the mean, and variance or standard deviation along these latent relevant dimensions. And of course, we want to be able to backpropagate gradients. A very interesting, not so old paper proposed a very simple idea, which is called domain-specific batch normalization. So it's possible to, with this method, you can do source-free domain annotation, unsupervised, and also online. So it ticks basically all the boxes. And the idea is very simple. You feed your segments for EEG data for your feature extractor. Then you route for each domain, so for each subject or for each day, the data to a specific batch normalization layer, which then can learn to recenter and rebias the data so that the data is going to be aligned. So very simple. And it's been actually shown to be quite effective in EEG classification problems, and actually in some competitions also. Okay, so we have this DSPN layer, which can align the mean and variance of different subjects or days. Okay, so how can we combine this with constraining the latent space to the SPD manifold? So we can use some neural network layers, which has been proposed for SPD, so SPD features. For example, one is to have still some sort of convolutional feature extractor, but then do, for example, covariance pooling, so compute covariance matrices along the temporal dimension, and then stabilize these to be sure that they are symmetric and positive definite with some simple thresholding of the eigenvalues. Then we have SPD representations. So how can we then generalize this alignment of the data and again project the data to a simple space so that we can apply a standard, very simple, for example, linear classification layer. And what we proposed actually is combining this idea of domain-specific batch normalization with some other recent advancements in batch normalization, also on the SPD manifold, to basically track the means, which are then on the SPD manifold or on Riemannian manifolds called Frechet means, and also variances across mini batches, while we still allow learning of the feature extractor. And then under some conditions, and in combination with some previous proposed layer, you can actually make sure or have some guarantee that these running estimates converge to the actual Frechet mean of the data set and also variance. And thereby, we have actually a bridge between this deep learning or geometric deep learning methods with this classic Riemannian geometry-based methods, specifically based on Tangermann space mapping. So this was probably a little dense, but just to give you an intuition of what the Tangermann space mapping and these classical methods do, I have here just a bit detailed slide, but not too detailed, I hope. So what we have, again, is the setting of Riemann manifolds, specifically the SPD manifold, defined with the finite variance metric. And we typically have a data set with coupled observations, so segments of EEG, with the associated labels. So, for example, a trial of EEG where a person performs multimetry of the right hand with the associated label. And what people do, they apply the feature extractor to project the data from the time series to the SPD manifold. Then they do this time and space mapping step, which consists of computing the Fréchet mean of the data and projecting the data back to Euclidean vector space, so standard linear space. They do this by solving this optimization problem for the data in this on the SPD manifold, and then project each point using a closed form solution onto this tangent space. The nice property of these tangent spaces is that the distance is again cheap to compute, so we're back in the standard linear vector space, and they locally approximate the infinite invariance, so they inherit the invariance properties of the manifold. However, okay, then you can do standard classification layer, for example, a support vector machine, the linear one. Problem is that these, because the Fréchet mean and variance are expensive to compute, people have been, in the last 10 years, have usually learned these 3 steps sequentially. So, and then you, of course, need domain knowledge to extract the features and so on. And what we have proposed recently is to learn the whole model in an end-to-end fashion. So use geometric deep learning to learn basically TSM. So again, we have an input space, some segments of EEG, some learnable feature extractor, which projects the data in a latent space. Then we have our explicit alignment data, alignment layer on the SPD manifold, plus this tangent space mapping operation, and a simple classifier, which is shared across the different domains. This whole model can then be learned in a straightforward way, actually, by minimizing for classification, cross-entropy error, for example, and you can use standard neural network training mechanisms to do the learning process, actually. For inference or for test time, you can keep the parameters of the feature extractor and the classifier fixed. Also for the source domains, then alignment layer. So you use the learned Fréchet mean and variance. And for new domains, so you can just project the new domain into this latent space, compute the Fréchet mean and variance, and then use this in the alignment layer, and then just apply the pre-trained or fixed classifier. If you want to do this in an online way, so if you can think of BCI, you can just apply, again, this idea of exponential smoothing to keep running estimates of Fréchet mean and variance of the newly arriving data for this new subject in your day. In terms of parameterization, we chose for the multi-imagery datasets a very simple architecture, which uses just temporal and spatial convolutions, basically shallow convnet, the first 3 layers of shallow convnet. Then there's this covariance pooling that I mentioned before, some stabilization to make sure that the data is SPD, and then our proposed alignment and tangent space mapping layer, and a simple linear classifier. The nice thing about this particular parameterization is that it's actually equivalent to this typical tangent space mapping methods, and thereby the model is actually globally interpretable, meaning that we can convert the learned parameters into spatial and spectral patterns. Okay, so now that we have all the ingredients kind of introduced, let's move on to some results for the unsupervised domain adaptation setting, specifically for intersubject and session transfer. For multi-imagery, we considered actually 5 datasets with a total of about 140 subjects, all publicly available. And here you can see basically the classification accuracy relative to baseline, which is the domain-specific model. So this is a model that has been fitted to the data of one of the session that we test our methods on. But it's like kind of the baseline that we want to achieve, like this gold standard approach. And we can see actually in intersession setting, our proposed approach can actually exceed the performance of this baseline method. Not so in the intersubject setting, which is of course the more difficult setting because you have much stronger distribution shifts. Still, compared to the other methods that we considered, we can still considerably decrease the gap to the domain-specific model. And if we look at the results for across datasets, for the intersession and also intersubject setting, we can see that the red method, which is our proposed method, performs well in the settings where you have scarce data, so very few observations, or where you have large amount of data. So in terms of robustness to data scarcity, this proposed method also has nice advantageous properties. So because the main ingredients are twofold. So first of all, use the SPD manifold and also do this latent data alignment. So we were wondering what drives this improvement. So we did some standard machine learning ablation study to kind of switch each contribution off. And we can see if we switch both off, the accuracy drops about 7% points, so quite a lot. And if we switch either SPD domain off or the alignment, we can see that the accuracy drops by around 4%. So both individual kind of extensions or contribution modules are quite important actually to explain the accuracy improvement. And lastly, I just want to give a brief outline or overview of what has the model actually learned, like to also close the gap to the first like spatial spectral kind of effects that we are interested on. So for multimetry, what we can do, we can convert these patterns, these parameters that we've learned into interpretable patterns. And for each class, we would get a set of sources. And if we look at the most contributing source, which contributed mostly to classification result, we see in terms of a spectral pattern, a peak in the lower alpha frequency range, and it's localized in central motor areas, which is what we would actually expect if you think about field multimetry. For left hand, we see even stronger kind of peak, localized peak in the alpha frequency band, and localized in the contralateral motor area, also what we expect, and likewise for the right hand. So in this setting, the model has obviously learned something meaningful that is consistent with prior literature. Okay, so to sum up, we can now learn interpretable tangle space method in an end-to-end fashion. And also with using this explicit alignment can improve generalization across sessions and subjects. Compared to previous methods, also component-based, but geometry-aware methods, but also deep learning methods, we can see a systematic performance increase. And this, due to the nature of the unsupervised adaptation process, this adaptation can be done online or in an unsupervised fashion. Of course, there's always some drawbacks. So computationally, it's not so cheap because all these operations on the SP manifold involve eigendecomposition. So if you kind of want to prefer to have a low-dimensional latent space, because the computation cost is cubic in this dimensionality. And by using this explicit alignment, you also make an assumption that the label or target distribution is similar across different domains, which might be, of course, not the case in all the problem settings. Okay, so I hope I didn't talk too long, but thank you very much. And I acknowledge all my coworkers, the ATR and Riken. And of course, if you're interested in this topic, please let me know. We're always happy to start collaborations, so I receive some interns and so on, have some visitors. Thank you very much.
Thank you very much, Reinmar, for this great presentation. So as we did yesterday, we are not having like 10 minutes of local brainstorming, so just give you some time to have a coffee, just to warm up a little bit, because since you're doing your presentation from Japan, perhaps you'll be tired. So thank you again for participating to this great conference. So now we are launching the brainstorming, and then we're going back in 10 minutes for like preparing some questions for you. So be prepared. Mm-hmm. See you in 10 minutes. Hi again. So now we have a very nice number of questions for you, Reinmar. Are you here?
Yes, I am here.
Are you ready?
Yeah.
Yeah.
Oh, okay, sorry. That was a bit of a delay.
Awesome.
But I hope you can hear me and see me.
Yes, it's perfect. So the very first question actually was asked by Theresa. Thank you for your question. So the question was about how can we use these methods in an online experiment? No, because there's this burning question about applying such super sophisticated methods in a real time. So you have some elements of answers?
Yeah. So the method itself, even though we use deep learning, kind of deep learning framework to learn it end-to-end, the architecture itself is very simple. It's like a standard TSM model, so Riemann geometric-based model. So it's very easy in terms of computations once the model is fitted. And then you can have very fast tests or inference. And if you want to adapt online, the only thing you need to track is kind of a mean and variance. Even though it's on a SPD manifold, it's still very simple. And you can do this very effectively. We haven't done it online yet, but the steps there is really not really big of an issue, I would say.
Awesome.
So simulated online, I've already done some experiments. All this adaptation seems to be working quite well. But of course, in BCI, you need to show it in a
and you have not so much time to actually perform the classification and provide information to the user. And then there is also the running question about how fast you can provide the information to the user without engendering some boredom, for the subject.
Yes.
Awesome.
So this talk was really focused on the machine learning aspects on the decoder, but all the other, like 50% or more of BCI, hopefully the other talks cover.
No, but it's really nice because it's a transition to the other talks we have later on about its application. So another question from Bournemouth about the interpretability of Riemann geometry approaches.
Mm-hmm.
So you already showed some elements about the features selected and the allocation, but you have any more information on that?
Yeah, I mean, we have to be a bit specific about the interpretation. The thing is, Riemann geometry or this tangent-space mapping has been used in many different variants. And for some specific family, the one that I introduced, with which use a linear classifier after this tangent-space mapping, you can get interpretation because they are consistent with a certain generative model that is neurophysiologically plausible. So for this, there are papers out there, and I think I've also put them on the GitHub page for this session.
Awesome, thank you.
Just check out the GitHub page. You will find the references there.
Yeah, because I saw some work from Barachan in which they are selecting specific channels to perform the classification to see which are the most relevant channels for the classification. It was the other way around, I would say.
Yeah, you can. There are many ways to get interpretation, but actually, what you can do for certain subfamily of Riemann geometric methods, you can translate the pattern, the source, or like the parameters into patterns.
Then we have a question from Lyon. Could you have more precisions about class imbalance performances?
I read this question also, but I'm not 100% sure about the formulation. So I guess it was about this limitation that I mentioned. And the thing is, so in multimetry, often we have like same number of classes for each subject, like it's balanced by design or has like the same imbalance by design. But if you think about more other settings where you have, for example, another neurophysiological signal, for example, what I'm studying right now is fMRI and EEG simultaneously recorded, and we maybe want to predict something from fMRI. This can be quite different in terms of the label distribution for each subject. So one subject can have maybe much higher ratio of certain class or target than others. And then if your effect is also in these power modulations, and you kind of align and remove this, align this means, then you kind of reduce your effect or attenuate it. So I don't yet have empirical results in this aspect, but in terms of like theory, there's a clear limitation which needs to be addressed.
Exactly. No, but it's super interesting, specifically for some specific application in which you don't have enough information from one condition, but more for another condition. Perhaps one, final but double question for you. One from Frankfurt about how many sources electrodes do we need? And perhaps related to this question, another one from Regensburg, in which they're asking how much data is required for training the model. So perhaps in terms of number of trials, I guess. So sources, electrodes, and trials.
So in terms of number of trials, based on my experience with motor measuring mostly, there is not much data required actually. So you have seen maybe in the LEAD 2019 datasets, they only have 50 trials per class per session, so which is not much. And even there, it works quite like state of the art. So, and it scales also nicely to larger datasets where you have much more, like tenfold number of trials. And so that's on the kind of trial aspect. On the other hand, in terms of sources, Riemann and geometric-based methods usually work better if you have a bit more channels, usually. I don't know a specific paper which really investigated in detail what's like the best trade-off. And I think for our analysis, we used mostly like something in range from 20 to maybe 40, 50 channels or so in input space. So that's a question I don't yet have a definite answer, I would say. But definitely, just very few channels is not ideal for
It's true. Perhaps we also need to find a trade-off, because I heard that even from the randometry approach, you need also to not having like huge covariance matrices. So you need to find a trade-off, but having enough information, but not too many, because otherwise you may have like poor performances.
Yeah, but that's like also a key point of using a feature extractor, a learnable feature extractor, because this feature extractor can learn some spectral filters, because spectral channels are also interesting, because we know EEG has different frequency and different oscillations, not only spatial channels, so you can think of some spectral channels as well.
It's true, and perhaps through the different approaches mentioned, but dimensional reduction, you can reduce the information, but you'll be focused only on the most relevant ones. I think we finished the very first set of questions for you. Thank you again for your presentation. So we're moving to the next talk, but be still with us for the discussion afterwards. Thank you again for your presentation.
Arigatou gozaimasu.
So now we're moving, with very first nice overview, but deepening approaches for BCI. We're moving now to another challenge to overcome, that is a small quantity of data, with the second talk by Michael Tangermann, who is an associate professor at Department Artificial Intelligence at Donders Institute at Nijmegen in the Netherlands. He's interested in transfer learning approaches and data augmentation, and his team translates the method developed into neurotechnological applications for clinical and non-clinical purposes, such as, for instance, language rehabilitation after stroke. Michael, the floor is yours if you're here. You can share your screen whenever you want.
Good. Yeah. Thanks a lot for inviting me to this really interesting format of presentations around, mostly analysis and working with EEG data. And today, with a focus on context of BCIs, brain computer interfaces. I thought I'd spend my time slot for a topic that is, keeping me in quite some unrest since a couple of years. That is that. We typically face a very challenging situation in BCI compared to other machine learning areas. That is that we don't have a lot of data, not a lot of training data points to learn from, or if you want to do online learning or unsupervised learning, also like the amount of data points usually is relatively low. The work I'm presenting today is a contribution of many of my lab members. I'll go into this a bit later in the talk. But I'm happy to show what has been developed in my lab in Nijmegen and also at Freiburg University, where I was up to 2.5 years ago. So we're talking, just to give you the context, mostly about the part of the BCI pipeline where it's about extracting features and classifying brain signals in order to drive some applications, of course. You did see examples briefly, and this morning here in the local garden in Nijmegen, we also looked at some examples, but I may repeat them for you to get everybody onto the same level. I will not be talking about brain signal features like oscillatory features that were in the focus of Reinmar's talk just before, but rather concentrate onto so-called event related potentials, also abbreviated as ERP, which can be evoked by visual, auditory, haptic, or other kind of stimuli, by noise-taking protocols, code-modulated protocols. There's different options that we have, but they all have in common that either by being like a physical deviant, like a lower tone in a sequence of higher tones, or by instruction that I give you different tones and tell you, please attend to one of the tones, there can an ERP be elicited. Let's see, this is the time axis, 800 milliseconds. And if this first tone presented here is a so-called target tone, like the one I asked you to attend, or that is indeed somehow different from the other tones, then the response in terms of microvolt potentials that I can harvest from multiple channels of the EEG differs for those target compared to other not attended, ignored, non-target tones. Okay, so attentive processing makes a difference here. This can be put to work in different BCI applications where a user interface plays a huge role. What I just showed you was an auditory one, so we also have auditory applications for spelling and so on. But the most well-known versions may be actually spelling applications where in matrices you have symbols that you can select, be that letters for really spelling, or be that maybe chess pieces on a chessboard, or be that other symbols that, you know, once you select them, they elicit some action. This, for example, is a photo browser application in order to like share photos with somebody or whatever. And let's look into one of these applications. So this is the photo browser application, and just for you to know how these visual events look like or can look like, this is an example that is very close to the original row column spelling. So we highlight in a sequence of events either rows or columns of that matrix. I hope the video comes through a bit so that you see that, you know, if you concentrate your visual attention, for example, to that tree and the sunset or sunrise, every time the corresponding first column or fourth row is highlighted, you expect a different kind of brain response compared to if any other column or any other row is being highlighted. We know we can get a substantial increase of the evoked potentials if we slightly modify the experimental protocols such that you do an overlay with, for example, famous faces. This has been investigated by colleagues from Würzburg University, or simply by having a colored grid that has a high contrast, a bit of movement, and go away from the indeed suboptimal row column sets that we're highlighting, but using a bit more clever selection of pseudo-random sets. Okay, but this just as a side note, overall, we can improve the saliency of these stimuli with the effect that also the evoked event-related potentials are larger, have a higher signal-to-noise ratio. And this, of course, I would now state is the first step. If you really are in a small data domain, try to get as good data as you can, like as high signal-to-noise ratio as is possible. But very often your experimental protocols may be fixed in some way because you want to reproduce a certain setup, for example, and you don't want to or cannot change the experimental parameters. So we're continuing now to look at scenarios where we cannot change these experimental parameters, but maybe we can do something on the decoding side. So a typical decoding approach that is used for these target versus non-target classification of epochs, and this is like attended target versus ignored non-target events. A typical feature that we can see there are that depending on the channels and on the time intervals indicated here by gray, by these gray boxes in the background, we can harvest something like an early negative, more negative component upon a target stimulus here in pink compared to the non-target in black, or a more positive response, also known as a P300 response for these oddball-like protocols around central areas So you probably know about these. Now, how can we now train a classification approach? The first, and I would say still state-of-the-art approach, is to extract the average potential from a few of these time windows, maybe not necessarily just 2, but maybe 5 or 10 of these time windows. And we do this for all the channels that we have available. So we may have 10 times the number of channels as features, and we try to discriminate them by a linear discriminant analysis, a linear model that lends itself very well to these kind of data, because the noise structure that we expect, at least as long as we don't have too many outliers in forms of artifacts, fulfill quite well the requirements of this linear model class. So actually, that's the optimal solution you can get, assuming that you don't have any disturbances in the data, which of course is not perfectly true. Another approach that directly connects now to what Reinmar has introduced in his talk would be per single data point, per epoch, like using these, 800 milliseconds of data to create a covariance matrix and consider such a matrix as a single data point that is either then target or non-target data point, example, stimulus. Or try to use this data in more raw form, do an end-to-end learning as indicated by Reinmar. Then we are in the domain of some deep neural networks. Alrighty. I'll stick to the first version with the LDA, that is also the most simplest, and show you what we can tweak out of this old lady. So, to get you on the same page, I have now given example time series that we record from 4 different EEG channels, all somewhere around the sensory motor areas, called C1 to C4. And I have indicated with these vertical bars that something is happening in the experimental protocol. So either we have stimulus of type 1 or stimulus of type 2. So that could be a target or non-target stimulus, one of them being attended, the other one ignored, right? And for those time intervals indicated here, T1 to T3, I'm sorry, T3 may not be readable very well, but you can think of these time intervals just corresponding, for example, to this early N150 or a P300 or other time intervals. We average the values that we measure here, that we sample, and create a matrix that is for every of these epochs, for every stimulus, indicated here by the corresponding label, whether that's class 1 or class 2. We have a vector now organized either by having all the 3 features per channel, and the next channel, next channel, next channel, or we do something like a time-first orientation of our data that doesn't actually matter. The content is the same, but it's more convenient to look at it in a moment from now. Good. So this is our training data. 4 examples, not very much. Typically, we do have a few more epochs to train our classifier from, but in this toy example, it will do for the moment. Then what does the LDA actually do? Doing the linear discriminant analysis. Now, in the end, we're trying to optimizing, for example, a Fisher criterion that tries to find a projection direction indicated here by this red hyperplane that we try to learn, that more or less separates these data distributions of class 1 and class 2. But this hyperplane basically, for us, defines a projection direction. So every data point is being projected in that direction parallel to that red hyperplane, such that in a lower dimensional space, indicated here just by this green line, we would be able to then make a class decision by just optimizing for a bias, okay? And what do we need for this? We need the direction of that projection, that is defined by the normal vector W, that is perpendicular to that red function that we want to learn, okay? So we need to learn this normal vector W and a bias B based on the training data. So in order to be able to do so, we have to make a few assumptions that the data has a Gaussian distribution per class, and that's even the same Gaussian distribution, each of the classes. And in the very simplified scenario where we assume balanced classes, W indeed can be obtained very simply by subtracting the class means and computing the covariance matrix. And unfortunately, also, we have to invert take the inverse of the covariance matrix. And this is a bit a tricky thing, as you can imagine. I mean, the means can be estimated also from a relatively small amount of data, typically, because the number of parameters that we need to estimate is just the dimensionality of the data. It can be a few hundred maybe, but it's not really killing us maybe. But estimating the covariance matrix, we're in the order O of dimensionality squared. Okay, I mean it is positive semi-definite, so it's a bit less than squared. But nevertheless, this is a problem, and inverting it also can lead to stability problems. Well, once we have determined W, we can use it indeed to compute the bias in a very simple way. All right, but now let's focus on this covariance matrix, because that seems to be a bottleneck. And indeed, we can do something here. So the state-of-the-art approach for a long time was indeed to, first of all, obtain the empirical covariance matrix. And after that, we don't really trust that covariance matrix, but we consider that this empirical covariance matrix may be here indicated by this red example here, that it could be shrinked towards a unit sphere. And if you trust our empirical covariance matrix a lot, then we don't shrink it a lot. But if we think, this is very unreliable data, we have very small amount of data points, maybe we want to shrink stronger towards the unit sphere, and by that strongly regularize this covariance matrix, as we have not a lot of data. This approach was proposed by Benjamin Plankert's and colleagues quite a few years ago now, but it still performs really, really well and is super simple. So when do we face now these extremely small data sets? That's as locally discussed here in the garden already. But if you, for example, want to try out different experimental conditions and make a decision, hey, I have a new subject, should I be speeding up my stimuli a bit or slow them down? Should I use a stronger contrast or not? Like, what is optimal for an individual new BCI user? And then, of course, I cannot collect like half an hour of data or not even 15 minutes of data in order to make a decision on this. But very small amount of data must be sufficient in order to make a decision about the experimental design that I want to use, like the protocol that I want to use. And my student, Chiara Töni, has just recently finished her master's thesis on this, how that even can be done in closed loop with having the user in the loop, and has proposed Bayesian optimization approaches for that, which works very nicely, at least in simulation so far. The other scenario would be that you have a patient for whom you can only work for limited time because of it's a problem with the stamina or attention, such that in order for the patient to have a chance to actually use the interface, like spell some text and write a message to a friend, you cannot record labeled training data for the first 15 minutes, because then there's nearly no time left afterwards for what you actually want to do, right? And the third reason may be, also indicated by Reinmar briefly, that if our data shows changes over time, let's say patient gets more tired over time, which also changes the brain signals, that means the feature distributions undergo some rotation, some shift. Anything can happen really. And if we need too much time in order to, again, measure label training data in order to update a classifier, that's also a no-go. So with the less data I can get along for that, that is very beneficial. And not to mention scenarios where I, want to, for example, train a patient after stroke to make better use of his language network, where I expect that if the rehabilitation training is successful, I expect that the brain signals should and must change over time, right? So this is a non-stationarity that I want to provoke that even in a scenario. Okay, good. So multiple reasons what we can do, and I will propose to you 3 possible solutions now. All of them provide solutions for ERP datasets, not for oscillatory data. And I'll directly dive into the first one. So let's assume the following scenario. We have 78 epochs only. So 78 tones are being presented, 13 high-pitched target tones, 65 low-pitched non-target tones, for example. And we have 155 features that we extract from our 31 EEG channels and, let's say, 5 time windows, TI. Okay, and we organize it in this channel prime order, like channels first. Good. Now, this shrinkage regularization by Blankets et al. Works okay-ish already. So classification accuracy for these extremely small training data sets, it's just basically one trial, like what the data you would record to typically just make one selection, like getting one letter from this matrix, right? This is about the amount of data we're talking about. Can we actually do better than shrinkage regularization? This is the covariance matrix that we're dealing about, and obviously that is like the problematic case. We have a spatial submatrix here that describes the relationship of the 31 channels to each other. So this is 31 by 31. That is for the first time interval, for the second time interval, and so on. And these other blocks that are a bit outside of the covariance of the diagonal, they would describe as how do those 31 channels interact with each other from one time interval to the next time interval, okay? So this is how you read these covariance matrices. As a reminder, we compute these covariance matrices from mean-free data. That means we do subtract here the class means, which means I actually subtract the ERP response. The background noise may still be like zero mean anyway, hopefully, like if there's no artifacts, but the ERP responses like a P300, of course they are not, right? And if I'm lucky with this strategy here to compute the covariance matrix, I'm actually extracting and removing the means firsthand. So you can look at the covariance matrix as a description of the background activity, or all of the noise, all of the remaining brain activity that you're not interested in terms of classifying target to non-target events. So now this nice assumption given artifact-free data. But let me now set up two domain-specific assumptions, and I'll hope I can convince you that they are useful to improve our covariance matrix. The first one, A1, is that the noise that is on top of the ERP responses is normally distributed. I mean, not many people would argue against that if you don't have artifacts. Also, Benjamin Blankert posed his assumptions on this, and I think it's widely accepted. So we don't need to go into that or in the discussion, maybe if you like. The second one is more interesting, I think. That is, the background activity, this background noise, is not related to the current task. So no matter if I'm in a resting state, or if I'm listening to a target, or to a non-target sound, or if I see a target or a non-target stimulus on my screen in front of me, if I subtract the influence of the evoked potentials, what is remaining is kind of the same amount and characteristic of noise. Okay? Would you agree on this? That's the people in this room. Raise your hand if you object. Oh, nobody dares. Let's see. You should dare me. So let's check this assumption. What we can do is now we're cutting our continuous brain signal recording into epochs. So again, this would be like 1 second after presenting the stimulus here at the black vertical line. And you see the target and non-target responses like averaged over many repetitions, just for the purpose of checking our assumptions. We have now a lot of examples. And we can, of course, also plot the standard deviation of this data, okay? Now we see that up to little wiggles here, I think the assumption is quite well given. Not so, though, if I do a typical pre-processing step, and that's very interesting because a lot of people do this when they work with epochs. They first of all baseline the data. So they enforce that in a certain time interval, the data is zero mean, which usually helps to make the ERP peaks nicely visible if you just want to visualize the data. But indeed, it introduces non-stationarity or a heteroscedastic noise structure. So the noise is not, background noise is not everywhere the same because of this interference that you do here. All right. You can avoid, though, the use of a baseline correction by simply using a high-pass filtering or by detrending your data. So there's options. We don't need it, right? But it's still contained in a lot of pipelines, analysis pipelines. Okay, so next thing is we're looking at our conventional covariance data. This is like 155 by 155, like 5 times 31. And we somehow see that these sub-blocks look a bit similar, even though in different intensities. Right? They seem to be scaled a bit differently. So what does that tell us? And this covariance matrix has been computed from our example data, where we have the number of epochs here. Every row is an epoch, like 78 epochs. And the dimensionality is 155. Assuming, though, that the noise is the same no matter in which time interval we are, we could say, hey, look, the first time interval and the second time interval is independent of each other. It was just indicated 3 more minutes, is this correct? Or, yeah? Then I have to speed up a lot. What I would like to indicate you only is that we can virtually decompose these 5 different time intervals into independent epochs and deal with it as if I have 5 times numbers of epochs, and so 390 examples that only have a dimensionality of 31. From this, I can compute a empirical covariance matrix that probably is estimated much better than what we had before, and I can use it in order to replace, after some scaling according to the determinants, these subblocks here. This is the actual trick of the so-called time-decoupled LDA, and it leads to much improved performances compared to the typical shrinkage approaches indicated here, or also to the Reinmar specific flavor of Riemannian approaches that we used for classification of these ERP datasets. I'll skip that and also show to you that the positive influence of this time-decoupled LDA is even better if we have small datasets. So if you have really large datasets, more to the right, these are all datasets from MOAB. I think the benefit of this time-decoupled LDA compared to shrinkage LDA goes towards 0, but you see it also does not hurt the classification accuracy. The same story you will actually hear, or maybe not hear completely anymore due to time reasons, for a second version that is so-called block triplets with tapering flavor of LDA. I'll directly go into the assumptions. That is, the background noise is assumed to be stationary in the sense that the covariance between 2 time intervals, the same channel, for example, only depends on their temporal distance, no matter if I extract them at the beginning of an epoch or at the end of an epoch. Okay, and I also assume that this autocorrelation over time goes towards 0 if I make this time interval larger and larger. I can check this, but I don't show this to you for time reasons now. But the idea now for this block triplets LDA is very simple. We can now argue that the same temporal distances within that covariance matrix, that large one, 155 by 155, are either within each of these time intervals, like within T1 or within T2, but also we could say like, the relation between the time interval 1 to 2 should be the same, like from 2 to 3 or 3 to 4. So basically, it depends on how much time difference we have between the samples in order to determine the background noise, which is expressed here by the covariance matrix. By this, we can assume that all of these in the main diagonal would have a delay of 0 should actually be the same, even though they may not be due to some noise in data or something. And also, these in the one-off diagonal should be the same, and those should be the same, and those should be the same, and overall they should be the same, up to some scaling. And this is indeed what we can introduce by looking at the empirical covariance matrix and then averaging along these different colors, such that we drastically reduce also the degrees of freedom of that covariance matrix estimation. Long story short, I get quite an enhancement also for extremely small training data sets, and go from the, in orange, standard shrinkage LDA that I introduced before as state of the art, with to the time decoupled and also then the block triplets in blue here. So it profits a lot from this improvement of the covariance matrix. I can really basically get along with half the amount of data that I needed to get to the same performance level before. Right? This is a comparison for a spelling application. The yellow letters are spelled wrongly, the blue ones are spelled correctly, different subjects. And we see that using this block triplets approach really improves a lot on the application level domain also. So good. All right. If I have 2 more minutes, if you would allow this to me, I'll go into like the hottest topic that has been developed in my lab, but I also could cut short here because I have a poster outside. So please let me know. Thumb up or down. All right. 1 minute. Okay, that's challenging. The third version I would like to propose to you is not really a machine learning method per se, I would say. It is unsupervised and follows this. I just show you the idea of it. Assume we have 4 or 5 different letters, and letter B is the attended one. This is my feature space, potentially high dimensional. I can now look at this situation to, like, I need to classify this letter B just based on those 78 epochs. I could make the assumption that all the letters A, C, D, E that are like not target, somehow, if I would compute their mean, this mean, this is that case, this mean should have a relatively large distance from all of the examples of the true target, because that target is different, it has a different mean, despite of all the noise that we have. So we can make different hypotheses. I make the hypothesis that B is the target, and then this difference vector between the means should be relatively large. While if I have the wrong hypothesis, for example, that letter A is the target, then the mean difference is relatively short. With this trick and a distance metric that considers the distribution structures, so it needs to know about the covariance matrices, for which I use the block triplets estimate to get a really good covariance estimate. I have a new method that's called unsupervised mean difference maximization. And this is how we can spell with it. So basically, close to 0 spelling errors on visual evoked potential protocols. On auditory, it's still a bit harder, but we can get at least on par with supervised methods. Even though it's unsupervised, it trains up from the beginning based without any labeled training data. This is also my wrap up then. So we need solutions for small data regimes in BCI. I proposed novel LDA variants, and I think they are competitive. And I'm very happy to really put them to competition also with deep learning approaches or Riemannian approaches. And with UMM specifically, we have a novel unsupervised classification approach that is completely omitting calibration. It omits a warm-up period. It mitigates non-stationarity, as basically it doesn't need to be trained on a history of data, but it does profit from history if it provided with. And it actually also comes with a confidence metric, so we can also see when things are going wrong. The code is available. Please approach me for the different methods. I wanted to point out how this talk refers to earlier talks today and the one by Hubert Bonville on Thursday, but I think it's getting clear. Thanks a lot to my team. Most of the work I presented was developed together with Jan Sosulski, my PhD student from Freiburg. I'm very thankful for funding that I receive. And of course, I'm even more curious about your questions now and later in the global round. Thank you.
Hi again. So we have many questions for you, Michael. The first one will be from Theresa. She's asking, why should we assume that the EEG unrelated to the ERP does not contain information related to the task?
Okay, this is an assumption that indeed I made. What I interpret this question as, when you say, is it unrelated to the task, is that indeed for ERP responses, if we only assume that the task elicits ERP responses, that we can describe these ERP responses perfectly by changes of the class means. So in some channels, at some time intervals, we have higher amplitudes or lower amplitudes of these voltage values. So this corresponds in the feature space to just different class means. Except for these different class means, everything else is just noise. Like assuming this standard model of EEG, indeed, yes, you can assume that everything that is unrelated to our evoked potentials is just background that is not providing information. But this limits the view just to these evoked potentials, right? If that same task also changes some oscillatory background activity or the coherence between some channels or some sources that potentially also could be exploited to decode the task, then this is not covered.
Okay, thank you. We have another question from Reinmar. He's asking, did you test how the performance degrades in the presence of artifacts? How would you improve its robustness to them?
Yeah, so in the data that I presented, but only too fast, these were real data sets, like most of them from WAP and a few from our lab, recorded partially from patients, partially from healthy users. We did not remove artifacts here. So even though we made the assumption that removing the evoked potentials, we should have zero mean background activity, and that is actually stationary and so on. We know this assumption is actually disturbed by artifacts. In practice, we can work with this quite well, even though it may not be completely fulfilled in practice.
Thank you. I think we have perhaps a time for a third question from Dundee. Is background noise will actually stationary in real data? I think it's quite related to the previous question by Reinmar. So in your case, do you think that background noise could be stationary in real data?
It is stationary in real data for the time horizon of an epoch, which is, let's say, 1 second or so. We know it's not stationary when you look at larger time intervals.
Okay, I think we have just finished this session. Thank you again, Michael, for this great answers and this great presentation. We'll see you later for the discussion. So now I think it's time for a short break of 15 minutes. Hi again. So now we're going to move to the last talk of the day. So here, actually, after having seen some more machine learning approaches useful to work with small datasets, notably, we're going to one step further towards real-life scenarios with patients in particular. And I must say that it is an honor for us to have Theresa Vaughan with us today. She is a research scientist with 25 years of experience in clinical research studies. She has supervised the very first large-scale trial of independent home use of BCI by people with ALS. Her team has developed many tools, notably BCI 2000 software has been used by many people in the community, and also some tools and training tools for therapists, caregivers, and users. And I must say, on more personal note, that when I met her for the first time, I was stricken by her extreme kindness and support towards young researchers. So, she's a real source of inspiration for us. So, without further discussion, Theresa, the floor is yours.
Thank you. Now, I hope that I can successfully share my screen. Uh-oh. So do you see that, Marie-Constance?
Yeah, it's perfect. Thank you. You can go ahead. Thank you.
Okay, well, just a word first about my encounter with Marie-Constance, and thank you very much for organizing this session, and thanks to the Michael and Reinmar for They're very informative lectures that lead me very easily to my topic. But Marie-Constance was the head of a postdoc and student committee for about 2 years that I had the privilege of being involved in peripherally, and I've seen her many gifts. So, and not the least of which is organizing this symposium. So thank you, Marie. Okay, so who am I? I'm Theresa Vaughan, and I am a researcher at the National Center for Adaptive Neurotechnologies at the Stratton VA in Albany, New York. We spent many years at the New York State Department of Health at the Wadsworth Center. But now we have a 3-site center, one in Albany, one in Washington University at St. Louis, and the other at the Medical School of South Carolina. And we develop neurotechnologies for translation and particularly for rehabilitation. But in the first instance of translation, we developed a system using the P300 method previously discussed by my colleagues here this morning for communication and control. And I'm going to talk about some of the challenges of providing a system like that. So that's my question. And I have a picture here that I love, not just because I love the person in it who was a research coordinator for the multi-site trial that we had on this BCI that I'm discussing this morning, but also because of the clutter. So one of the challenges of doing this research is actually entering the homes of people who have very complex lives due to their severe disabilities. And I am by no means the first person to do this or the only person to do this, but in fact, I learned a great deal from Andrea Kubler in Tübingen and many others, including Michael, who has worked alongside me for some years, has applied his methods to people with aphasia, especially. So you can see there's barely room to stand, and you have laundry detergent on the table. You have feeding tube and respirator for people who can no longer move or breathe or eat on their own. And now we have a BCI, and we've talked a lot about these parts of the BCI, how we acquire a signal, in this case EEG, and how we might extract some features and translate those features into control using event-related responses. And I'm on the application end of this, and this in a model developed by my lab chief and my associate, John and Liz Wolpaw, where we think that BCI could be used in many cases to help replace, restore, enhance, supplement, improve, and now emulate, do research regarding how the central nervous system responds to stimulus. And that is in some ways demonstrated by the first two speakers. So here we want to know who could use a BCI for communication. And we've estimated that worldwide there might be over 100 million people who might use an EEG-based BCI for communication and control. And by control, I mean not just communication, but also controlling a computer to do various things. And these people run the gamut of neurological diseases, from cerebral palsy, something that's central and present usually from birth or early on, to something that's acquired like spinal cord injury, or something that's neurodegenerative like Parkinson's disease or amyotrophic lateral sclerosis, Lou Gehrig's disease. So the problem of communication for people who are paralyzed is one that's been solved by a number of different technologies, and these are grouped together in a class called augmentative and alternative communication. And basically, this big category of thing is anything other than speech for communication. So an alternate communication method for us, for people who are able-bodied, might be a keyboard, or it might be writing, it might be texting. But a well-designed AA system is flexible and adaptable and maximizes the individual's ability to communicate effectively and efficiently across environments and with a variety of communication partners. And that's from an article by Buchelman and Marinda in 2013. And really, that describes the challenge of using a BCI. Now, I want to pause here to say that even though we join a series of an AAC continuum that goes, as I mentioned, from keyboard to mouse to motor strip, motor switch that might react to a small movement, for instance, with Stephen Hawking's, where he retained a small movement in his cheek that he was able to activate a switch, or an eye tracker, very efficient for people who have almost no movement but can move their eyes reliably. But we are at the end of this continuum. Our BCI devices are important for people who can no longer move reliably in any way. So how does this translate? So first of all, can the people who need a BCI use yours? And I want to say that the most important thing in a BCI is a signal. And so throughout my talk, I want you to remember that we are recording EEG with the same kind of fealty, or at least we're attempting to do that were mentioned in the talks. And so the second question is, can BCI be implemented in a form suitable for long-term independent use? Does the BCI get used, and how? And does the BCI improve people's lives? And all of these questions are important for translation, but to some extent, they have to be answered with a specific device and with a specific signal. So acquiring a signal, a reliable signal that everybody has, or at least most people have, is one of the problems. And here we have a well-studied signal described by the previous speakers, an event-related response to the oddball or the attended response, the target in the paradigm. Here we have in an article by Sellers and Donchen, O's and X's, where the X is the rare, and as this is a visual task, and here we have a response in the EEG, target being the solid, and the dashed line, the non-target, and the difference, as was described so well by Michael in the previous talk, is where the information comes from for selection in a task that was described by Farwell and Donchen in 1988. So when Professor Tangermann says that this is an old woman, I will tell you it is. This is a method that represents a signal that can be recorded reliably in most of the population. And we know almost, as was described previously, without fail, how to elicit it. So this represents the grid that you saw earlier in the movie, those beautiful pictures where people were selecting icons. And here, I hope you can see the very simple grid that we chose to translate. And one of the shining principles of translating such technology is that you have a moment that is frozen in time. So this old chestnut, this P300 based speller that was described by Manny Donchin in 1988 and came out of 40, at that time, 30 years, but by now, 50 years, over 50 years of research on event-related responses, is doing a very simple task for this individual in the laboratory of using a predictive speller of selecting words and letters and words in the co-writer, what we call the co-writer. And so now I have my application. I have a signal that I can rely on, at least to the extent that without additional challenges in the laboratory, in healthy controls, I know works reliably, first time, every time, or with very few errors. So how does it translate? So the first question is, can the people who need a BCI use yours? And so now you have to find them. So who are they? Well, as you might suspect, people who cannot move might be people in coma, or people who cannot move reliably might be people with cerebral palsy, people with stroke, or people with ALS. And these were the people who we chose to work with. And there were a few reasons why. That includes, most importantly, that the people would meet the criteria of being stable otherwise medically, because this is a slow, usually this disease strikes people in their middle age, or I think the average age of diagnosis is 52, and they are going to live in a stable environment with relatively few changes from day to day. So these people also are people who previously spoke. And many of them understand how a computer works, especially now as it wasn't exactly true. They also have caregivers, and often caregivers 24 hours a day. And so these are people who can help with the doffing and donning of the equipment, turning on and off the system. These are the criteria. These were the criteria that we were looking for, that people would have a chronic disorder of voluntary movement, that they would have some remaining motor control. And that because we did not want to be in a situation where failure meant also no information. We wanted to know something about why we were succeeding and failing. And also we needed assent to the study. Conventional technologies weren't adequate. That is, that eye tracking at the time, or whatever switch was being used, were inadequate, unreliable, becoming unreliable, or unreliable completely. There was a stable environment, technically capable caregivers, although that proved not to be essential. Just caregivers became much more regular, and the realistic understanding that this is a study, research, and just pragmatically, where could we get to? So can they use it? Well, to answer that question, we deployed in clinics and in homes the system over the course of maybe 1 or 2 years to collect data on a large population of people with ALS at various levels of disability. Now, here is a beautiful example of a filtered P300 response, both in time, here this is 1 second along this line, and in space. This is the head, the nose is at the top, and this is the top topography of where we're recording. Now, we'll talk more about CAPS, but you can see that there are only 8 little dots on this head. And this is a statistic of target to non-target. So targets here are in red and non-targets are in green. And this is of the variance in the signal. So information in the signal that we can use for classification using a linear discriminant function, by the way. Very interested in all of those variations that Michael talked about earlier and in the geometry example given by Reinmar. And so here we have a response in people with ALS. And how does that look across the population? This is an individual. How does that look across the population? Here in ALS, the individuals receive a functional rating as their disease progresses, and it's a score of 50, and sometimes 48 or 52, depending on the type of scale that they're using, is completely able to control all motor function, and a score of 0 means that there is no controlled motor function remaining. So here we have on the y-axis 25 up to 25. So we try to measure across the spectrum of function. And so people who have a function of 25 would be in a wheelchair, no longer able to move their arms and legs, no longer able to dress themselves. Some would be able to speak, some not. And 0 would mean that people are respirated and have no remaining function except perhaps the movement of their eyes. So here we have the online accuracy of the speller, of using the speller that we saw in the movie, and we can see that this is at 100% and 0. A functional rating of 0. We have many people here who can use the system, some perfectly, some not so perfectly, but also people with higher functional scales. So we've identified a method here in this study that would be available to people with ALS, even when they had no remaining motor function. Now, these yellow circles indicate that there were some visual issues, and so we believe that one of this, obviously this is a visual system, it has visual stimulus, so this would be a reason to exclude someone, but their functional rating would not be. So we found that we can perhaps use this system we created in the laboratory with people with ALS, and now we want to know if it can be implemented in a form suitable for long-term independent use. And I want to emphasize again that the main question here is, can we get reliable signals, and can we get reliable signals that last over time? So the first thing is how to make a comfortable cap so that people can wear it all day. And we spent a great deal of time looking at different models. For our system, we chose a cap that uses 8 electrodes, and we did studies that reduced this method. The method in the lab originally used 64 sensors, and the home system used 8. We also used a wet cap, that is, this cap required gel. And we did this as opposed to dry caps. Here is a dry cap, and a cloth cap for comfort. Here is a cap that we designed that has individual in head measurement. But there were also snug. The electrodes should not be moved. The signals have to be reliable and long-lived. And the cap should be comfortable and easy to off and on. So that's before you get to the sensors. That's before you get to the EEG. So the hardware has to be portable, affordable, and here's a slide from my colleague Dennis McFarlane. This is actually where he started, or how computers looked when he first used them. When we developed the system, we used an IBM system that filled the room, not exactly like this, but filled the tabletop. But here we developed, because of laptops and because of advanced technology and amplifiers, we were able to put a system together that was portable and affordable. And now the question is, how do we use these data to help us understand how BCI for communication and control might be effective and maintain people's privacy and give them something useful and measure whether or not they use it on a day-to-day basis. And so this rather complicated picture of what I like to call BCI 360 is the environment that had to surround each of the users. We have this lovely application that we developed in the lab. It has to be useful to people. We had to develop diagnostics. We had to know and train caregivers to detect and understand what a good signal and what a bad signal was. And we had to do this in real time every day. And I mean that they had to be able to regard the signal and understand in some palpable fashion that this was a good signal and that they could go on and use the system. This was by no means the only challenge in the EEG, because and we'll discuss later how the user also interacts. So a BCI is an interaction between both the system and the user. So we developed, but also we had to have secure and regular understanding of if the system was available. We put in something called the heartbeat that we got every 15 minutes. And if this heartbeat was disrupted, we would understand that the system was no longer available, then we would give a call. We for the data daily so that we would understand if the system was in use, was it being used accurately? And of course, we kept track of which of the applications that we designed were being used. So something to use and training and support, of course, I mentioned it. So we had several applications. We had a simple communication where people could spell. We had email and several other applications that we'll discuss. And this is a picture of how we guided the caregivers through their signal setup. Here, of course, is the impedance measure. This was critical, but not essential to a good day or a bad day. But without reasonable impedance, without reasonable signals, without our. Now, let's just talk about collecting EEG in people who are paralyzed. We are going in to be something that would be quite straightforward. Respirators, for instance, create quite a bit of artifacts. Tubes create artifacts. All the mess that you saw, the cat jumping on the fire engine, the fan in the room, all of these things are challenges in signals, creating artifacts that could be conducted into the EEG. So finally, does the BCI get used? And here in our very first and really very important user, a guy who was very anxious to use the system and needed the system for his work with very advanced ALS. This is it stable? So the question over time is, does the P300 remain stable? Do we need to constantly calibrate the system? And in this case, we learned that we did not, that this signal is stable over time, very stable over months and years. And recalibration, although it definitely is essential as the disease progresses and in rapid progression, for people who are medically stable, this signal is pretty stable. Not this stable, really. This is a special condition. This is for paper. I mean, it wasn't like this every day, but you could find the same response month after month. And also, it could be used. So here you can see a slight downward slope as over the 800 days that this individual used the system. And you can see that there was a fair amount of daily variation. Here, for instance, perhaps there was some problem in the signal, but mostly this variation is not due to system failure. It is not due to bad signals. It is not due to poor calibration. It is due to something else, and it's not due to bad impedance. It is due to something endemic to the user's performance, and this is not yet well understood. So we got regular reports. We had to measure how it was used. I'm sure I'm almost at the end, and I'm almost at the end of the presentation. We followed 14 users, 8 without other means of computer control for 12 to 18 months. And here we have a pie chart, very colorful pie chart that indicates, for instance, how they used it. So this is communication. This is simple spelling. The red in the orange, that's email. In the green, we have a news reader, a static internet connection that allowed them to see news. Here we have YouTube, books on tape, and pictures, and the yellow is copy spelling. So that is there's two interesting things about this slide. One is you cannot develop a system without involving users, and the users should be in the lab. They should be endemic to every stage. Because here, I would have thought YouTube would be the thing that they use the most, and they used it the least. And what they did with this system was, in many times, controlling their daily lives. So here in an email, there was a description of how someone could run their lab. This is the guy whose data you saw. Some people used it to communicate. One user in particular used it for just 1 hour a day, used it 3 times a week with the caretaker present, but it was necessary for her to communicate autonomously. And they were various. In fact, the first time she said, "Speak louder." She was asked for care, they made appointments, organized social events, and in one case, over using the BCI for a very long time to develop letters and testimony for
excuse
court,
me, Theresa,
had power of attorney changed and obtained a divorce.
Theresa?
Yeah.
Excuse me, just to interrupt you. You just have like 3 minutes left before the end of your talk. Thank you.
Yeah, I'm done. So the way we see the near future for this device is that all the hardware getting easier, as you saw earlier, all of the classification methods getting better, automatic calibrations, telehealth. These are my folks who I love deeply and who I depend on or have depended on over the years. These are our funders and can support. And this is my dear dad.
Can you hear me?
I can hear you.
Okay. Thank you, Theresa, for this insightful talk. I mean, we're all super enthusiastic about this because it's super interesting and important actually to have insight about the actual translation towards clinical routine. Thank you again. So now. So we have actually a very nice number of questions for you, Theresa. So Leon asked, did you observe any long-term effect, positive or negative, of BCI use on cognitive abilities and EEG patterns?
So I think that the question is interesting from the perspective of whether or not BCI might either change a person's brain to the extent that it might do some harm, or it might benefit an individual to maintain contact with the world. I think both questions are still open, but we did not see any changes.
Thank you. Then we have a question from Nijmegen. The non-invasive BCI, as you present, it seems very valuable for users. What are the limitations that could prevent these systems from being usable outside research?
The small cohort. So the group of people who could use this do not encourage commercial development. As the technology changes and becomes more affordable, as there are more, so I had a lot of faith in Facebook. I was a little disappointed that they didn't come up with the killer app so that all of this stuff could be available. But I think one, just as an editorial, it's very important to keep in mind that we should not lose sight of this application as this technology goes forward. And I think you're right. Many people could use it.
Then we have like a common question, like quite related between the two. One from Bournemouth, are there ways to further speed up the spelling with BCI? And related to this question, one from Genova, how long do they take to complete a sentence?
So our system was pretty slow, and we used many repetitions to ensure that there was accuracy. So some people chose to speed up and be a little bit less accurate, some people, but sure. Almost everybody chose to have a long time between selections. So I don't think that, I think 24 selections in a minute was the most. I mean, typing, good typists can do over 100 strokes a minute. So it was pretty slow. But on the other hand, I think it was fairly easy to use and might provide the ability for people to initiate a conversation as opposed to just answering yes or no.
Yes, and so we can observe some variabilities between the patients, and perhaps you may observe some training effect.
Right.
Even at the individual level, you may observe some changes over time.
Right.
Perhaps the last question would be from Frankfurt. What can be achieved with 8 electrodes in general? So perhaps like the limitation, the benefits related to the number of electrodes you're using to perform your BCI training session.
Well, this is a very robust signal. And so 8 channels was, that was the whole thing. And people could use it to, do whatever a computer could allow them to. So we controlled, for instance, a smart apartment with it. So, things of that nature. I still have reservations about, for instance, moving through space reliably with a signal that's non-stationary. But I think with 8 electrodes in general, you could do everything you needed very slowly on a computer.
No, but it's important to keep in mind that the feasibility, especially with patients, because you don't have the time to have a full montage of 100 electrodes. So you need to keep in mind that the feasibility of your montage is true. So I think that we are not done for your questions, Theresa. Before moving to the last part for the discussion, I just wanted to provide some highlights about the different information provided by all speakers, and just to give some food for thought for all the gardens. If I can share my screen, I will try. I hope that it will work this time. Let's see. Awesome. This time it seems to work. So it was a picture I wanted to show you before, just to recap the 4 main steps while performing a BCI experiment. So just to remind you, the different limitations we observe, especially in terms of inter- and intra-subject variabilities. So it's true that perhaps historically most of the research was actually focused on the machine side by trying to improve the classification performance and also provide some more relevant feedback, for instance. But then there is also a growing interest by trying to, as mentioned by Theresa before, trying to understanding the mechanisms underlying the BCI performance and potentially training aspects. And this information can be also relevant to build potentially new features that could be relevant to perform BCI protocols afterwards. And another aspect also to be considered would be the human factors. By taking into account both the subject/patient and the experimenter's point of view. So this is just like a very brief overview of that, just to have in mind that BCI domain remains a very multidisciplinary one, and to tackle some issues, we need to adopt different perspectives to address the current issues.
It was a question from Cuba. They were asking, would it be useful to use a method even if the sources are found with nonlinear sources localization decomposition method?
So this is about this. I guess the question is related about this linear mixing model, the spatial mixing model that
I think so.
Yeah, I mean, that depends. I mean, for example, maybe not EEG, but in fMRI, we know that the mixing or the effect from brain activity, general brain activity, to the signal that we measure is actually nonlinear. So there's not a direct, and actually that's not so well understood. For EEG, there is like this linear spatial mixing. However, in terms of the temporal effect or spectral effect, the response could be, or the coupling could be highly nonlinear. So definitely nonlinear methods can have a huge potential depending on the, problem or a localized effect that you're interested in.
Thank you. So now let's go back to the general discussion for everyone. Okay, sorry. So we have one question from Nijmegen for everybody. We have seen in your talk and the local one by Nick Ramsey that patients use their BCI for years. We also heard from Michael that it is important to optimize the BCI development for little data. Can you comment on how a BCI system that works on little data would be of value to long-term patient use? So perhaps, Michael, you can start.
I'd like very much to comment on this. So it is great to see that Theresa, for example, reported that the BCI system that were used with the patients in Albany did not have to be recalibrated very often. And this is also what I took from the talk of Nick. Now, not having to recalibrate because you are content with the performance is one aspect. The other aspect would be like, maybe there's more to gain if indeed you would recalibrate. So maybe you could squeeze out the remaining 10% in accuracy that could get from it. So that's a trade-off, of course, like if you want to do that or not. The second aspect is, if non-stationarities, like changes of the signal quality over time, or of the signal characteristics over time, are part of the game, and we assume this is the case, like if a patient takes medication or does not, if a patient becomes more tired over the course of a session, has difficulty concentrating, or if there's distractions in the room. Theresa mentioned a lot of things that can happen in a patient's home, right? So these are external factors that change what you think you measure as a brain signal, but partially it's a mixture out of brain signals and external signals, or the brain signals do change. And to be able to adaptively react to that, you need to maybe change or adapt your decoder. So it could be beneficial to do that. We observe this at least in the context of training patients to rehabilitate, where we really want them to change the way how they activate their, let's say, language network, for example. It is, of course, obviously part of the game. If you think about progressive diseases, it may also make sense to update, but that happens usually on a much slower timescale. So I think the work I present are more, or that I did present, were more focusing on changes on the faster timescale, like tiredness and other factors that are kicking in and giving you a hard life.
Theresa, do you want to?
I couldn't agree more, actually. I think updating methods. So, for instance, when Kaufman published his paper on faces, we immediately switched. I mean, if there's a method that works better, you would have to recalibrate then, obviously. But also to have the information about let's say fatigue, for instance, you would have to have reliable information about that, and that would have to be part of the system. Reliable information about state is very challenging to come by. But I guess one other thing is that you know, your sense of how reliable a system is it depends on, as you say, on training. And so we're training something every day. We're training something, right? So we don't know exactly what it is. It's like 7th grade boys, you know, they're learning something in class, but we don't exactly know what it is. It might not be biology. So I think, you know, when we see people use the P300 over time, they get better at it. But what means better? Maybe better means they use it with more ease. Their attention, I mean, like learning how to drive. So I think things do change. I think, you know, nothing stays the same. But in terms of the system itself, being able to rely on the system to work when you wake it up to work, then I think you can, it's a stable signal.
Yes, Michael?
I would like to add to this, like the less complex a decoding system is and the smaller the amount of channels that you measure and so on, the less opportunity there is that your system goes down the road in case there's some external factor changing. So you more easily overfit if you have a very complex decoding system and a very complex measurement and then many channels and so on. So keeping it simple, I think, could really be helpful for robustness. Or if you actually have, let's say, a more complex recording and so on, that you strongly regularize. Oh, the second screen turned off.
We can still hear you.
I can still hear you.
Yeah, we got you.
So maybe it is indeed also the question, like how strongly you regularize. But you can actually also deal with these non-stationarities by collecting a lot of data and learning in maybe using representation learning, what is the invariant part of my signal space? Like, there may be a lot of factors influencing my signal. I sometimes have high noise in certain channels, whatever, but what is the underlying core feature that does not change? And these are invariance learning problems that we also deal with deep learning approaches. We say, like, maybe we want to become independent to sudden loss of a channel or high noise in a few channels at some point that can happen after you have the cap on. After a few hours, the gel dries out a bit, at least in some models, or that you get some other artifacts into the data, and we can learn to become independent, invariant to that, right? But that's a different way how to approach it.
Thanks. Very nice transition to Reinmar work actually with machine learning approaches.
Yeah, thank you, Michael. I just have maybe a follow-up comment or maybe my own perspective on trying to learn an invariant space. I mean, that sounds very good and great, but I don't know. I mean, I'm mostly talking about oscillations, so multimetry and in the context of BCI and so on. So even when you extract, let's say with a linear model, you extract the source activity, due to the lack of specificity, when you do multimetry, you know, even if you move the arm or foot, you still have some change in the power modulations, right? Or if you just have like general attention shift, maybe your alpha power goes up and down. So you have very unspecific signal, right? So even this patch of cortex in the motor area is affected by so many other factors, right? So even if even if you identify correctly the space, this is really kind of stationary in this sense. So it's still affected by so many other factors, right?
If I can reply directly, then of course, I don't think that perfect invariance is a goal that we can reasonably obtain, but we can try to become invariant to as many of these factors as possible. The question, of course, is often, did we already see all of the different problems that can arise? Like, even if you have like many days of recording with the same subject and the same protocol, at some point, the dog or the cat jumps onto the bed and it creates different kind of artifacts that we have never seen before, right?
Yeah.
So
that's the question, yeah, if it's systematic or if there's really basically a random noise process.
Then we have a question
I
from
think
Leon.
the respirator artifact is an example.
Yeah, can you repeat, please, Theresa? I didn't hear you well.
Oh, sorry. I just wanted to say respirator artifact is the perfect model for unpredictable noise in the signal, and it happens all the time, every day. You just can't regularize it. You can't identify it. You can't know when it's going to happen. It has so many factors, and it's just 12 times a second or 12 times a minute, right? I mean, you would think you could do something with it, but you can't. At least to date.
Oh, no, you're right.
Interesting.
Yes, then we have a question from Leon. Perhaps can you design machine learning algorithms that take into account the profile and characteristics of the user? So how to combine in the end, like both the machine and the user perspective to improve the BCI system in the end? I know, for instance, in deep learning methods, we could add some cognitive profiles, or not cognitive, something related to the user that could be relevant for the classification, for instance, or via Bayesian approaches or something like that.
So maybe, sorry, Michael, did you want to start the response?
Go ahead, Reinmar. But I'm curious on what you think.
Okay, so in the sense, the classic session subject-specific methods per se are user-specific, right? Because they just fit personally to the user. So in a very broad sense, or in terms of BCI. But of course, the methods that I was talking about have some general part, and then some very specific user part where we just try to kind of learn the current ongoing, more or less baseline activity, where we want to kind of see our relative effects. So in this sense, we try to incorporate this user specificness of the day. However, as we know, maybe if two people do multi-imagery, they probably perform the task a bit differently. So I still think there is quite some demand, and this is still, I think, especially from the representation learning, so deep learning perspective, I don't know yet the good approach that tries to really also embrace this and tries to maybe identify different stereotypes. The question is how much data we need to record to kind of get all these subtype stereotypes, whether they are there. So there's still a lot of open questions actually in this aspect.
Okay, so Reinmar, you answered this question in the sense of a transfer learning problem, right? So you're assuming recordings of 100 users of this doing the same experimental task or executing the same tasks, and then there's the 101st patient or participant, and you want to know, like, is this somehow a similar? Can we expect similar brain signals to one of the other ones, and maybe take a shortcut and just use one of these models? I think this works decently well. But I'm very tempted to actually expand this representation learning problem a bit to really metadata that we have. We know that brain signals change with age. We know that brain signals change under certain other conditions or under external factors. So maybe knowing a bit more about the users could be informative, but for this we would need to have way more data. So not a few tens of users, but maybe a few hundreds to a few thousands of users, all with metadata. And then I think we would have a realistic chance to learn, like to make better predictions for a new user where we haven't seen any brain signals from, but we know, for example, the age, or we know some other circumstances from a clinical record, for example, that we could probably deal with this patient's brain signals in a more beneficial way from the beginning than if we just start ad hoc.
Theresa, do you want to add some, perhaps Reinmar, if you want to answer?
No, I totally agree. So adding some external factors like age, as we all know, affects quite a bit brain signal activity and maybe some patient record and so on. Of course, this can be potentially very helpful.
Theresa, do you want to add something? Oh.
I think it's interesting whether or not, I mean, it's an interesting approach. So I guess, yeah, that's all I have to say. I'll think about it.
So we have perhaps the time for one last question. Yeah. So perhaps more like an open one from Bournemouth about whether natural language models like ChatGPT can be used to improve the systems. It's super fancy right now, so we need to ask about ChatGPT.
These models can be used for what? I didn't get the...
To improve the systems.
Okay, good.
BCI system, for example.
Well, I know that there'll be an algorithmic response that's more more tailored to the natural language model. Can speak to that, but I can say that one of the gold standards for augmentative communication would be to be able to be in the conversational space. So if I want to talk to you about the articles in the New York Times about, the baseball game or the soccer game or football game that was last night, I want to be in that conversational space. And I think for me, one of the coolest things about ChatGPT is I can be in that conversational space. I don't know if it's been applied yet, but this would cut down on it would give vocabulary, it would give context, it would allow you to speak directly to the issues.
I know, Michael?
The first thing that came to my mind now hearing this question was maybe the very limited communication bandwidth that is provided by a BCI, can in a post-processing step could be enhanced by such large language models, where you have a bit of output maybe containing also some errors. You ask the model to maybe clean this up, right? Which can go wrong, of course, but also these models know a lot about the world. Maybe not about the world and the context of a ALS patient being at home and other caregiving conditions. But in principle, I mean, you could blow up the complexity of your interaction with the world and with other people by providing only a bit of information with this low bandwidth channel BCI, and then basically making it more complex, making it more adapted to the situation by using a model that knows about your situation and knows about the world a bit. And maybe you can indicate just a few things, and the model takes care that you get an appointment done with your GP next week, but not on Thursday afternoon, because that's always when your aunt is visiting or something like this.
Yeah, maybe I've just also, I was also thinking more or less in this direction, but because in this sense, ChatGPT and all this language model, LLMs try to predict the next element in a sequence, right? Given some prior context. So you could maybe use it also in some extent as a next token or character prediction or word prediction or integrated in a kind of BCI speller. That's like my
yeah, that's very low-hanging fruit. I think their capability goes beyond that in the meantime, but that would be an easy catch, I think, yes.
Mm.
Well, thank you very much, actually, for this very nice discussion. We'll try to gather all the questions afterwards and put in dedicated documents and write some answers for those who, unfortunately, we didn't have the time to address them. I would like to thank you again, the speakers, for their wonderful talks, and we are super happy to have a dedicated BCI session for this Cutting Garden. So thank you all, Theresa, Reinmar, and Michael. And this is time to actually, call it a day, I think. Unless Max has or Adrien some information? No, if not, thank you again, and see you tomorrow for another session. Bye-bye.
Bye-bye, thank you.
Thank you.
Bye-bye.
Thank you all. Thanks very much.